Very good morning to all of you. Welcome to my YouTube channel. Today I am going to teach you Rolle's theorem. So this theorem was given by the French mathematician Michael Rolles in 1691. This theorem states that if a function f is continuous in the closed interval ab, derivable in the open interval ab, and also the value of the function at a is equal to the value of the function at b, then there exists at least one real number c which belongs to this open interval ab such that f dash c is equal to 0. So if these three conditions are satisfied, we can say that Rolle's theorem is verified. If any of the condition is not satisfied, then Rolle's theorem fails. So next is the geometrical interpretation of Rolle's theorem. So from the figure A, it has been clearly observed that there is no gap for the curve y is equal to f of x from the point A to B. So if there is no gap, means there is no breakage, or we can say discontinuity from point A to point B, this means that the function is continuous. Also, there exists a tangent for every intermediate point between A and B. Also, the ordinates A and B are same. So then by Rolle's theorem, there exists basically one point C in between A and B such that the tangent C is parallel to the x-axis. So this is the basically the geometrical interpretation of the Rolle's theorem. Next, I will prove the theorem. So for proof, two cases arises. First case is that if function is constant function in closed interval AB. So and second case will be if f is not a constant function in closed interval AB. So if f is a constant function in closed interval ab, this means that the derivative of the function is equal to 0, because we know that the derivative of a constant function is 0. So where I will write where for all x belongs to open interval ab. So this also implies that if f dash x is equal to 0, this means that f dash c is also equal to 0. I am replacing x by c. So here I will write for all c belongs to the open interval AB. So therefore, the result is true in this case. I will write the result is true in this case. In this case. So next case will be, so case second is, if f is not a constant function, not a constant function throughout the closed interval AB, out the closed interval AB. So if f is not a constant function throughout the closed interval AB, this implies that f is continuous in closed interval AB. So this implies f is continuous in the closed interval AB. So if f is continuous in the closed interval AB, so this implies f is bounded. So f is bounded also. So if f is bounded, this means it attains least upper bound and greatest lower bound, means it attains maxima and minima. So I will write this implies that f attains, this function attains least upper bound and greatest lower bound in the closed interval AB. So basically least upper bound is the smallest element in the upper bounds. Okay. So similarly greatest lower bound is the greatest element in the upper bounds. Now what happens? Now we are taking that f is not a constant function. So I will write as, since f is not a constant function, not a constant function. So if f is not constant function, then what happens? Then at least one of these bounds must be different from the values of f of a and f of b. So I will write, therefore at least one of these bounds means least upper bound and greatest lower bound, least upper bound and greatest lower bound, or I can say maxima and minima. Okay, so least upper bound and greatest lower bound must be different from the equal values of f of a and b. Equal values of f of a comma f of b. So now I will take that this bound, let this bound be attained at some point. So let this bound be attained at x is equal to c, say, where c is different from a and b, where c is different from a and b. That means c belongs to the open interval ab. Okay, so now what happens? So I will write, without loss of generality, without loss of generality, we assume that, what we will assume? That this least upper bound, which one? This one, that is least upper bound of this function f, is attained at x is equal to c. So what I am assuming, that this least lower bound of the function f is attained at x is equal to c. So therefore I will write f of c plus h, this is less than equal to f of c, where c plus h is any point in the neighborhood of c, and h may be positive or negative. H may be positive or negative. Okay. Now, for example, now what we have to show that, now I am going to show that if h is positive, that what happens, and then if h is negative, then what happens. So I will write, for example, if h is greater than 0, means h is positive quantity, then this quantity, above quantity, f of c plus h minus f of c, this is less than 0 divided by h. Okay, similarly this implies limit h tends to 0 positive, because here h is greater than 0, so I am writing it in limit form. So limit h tends to 0 positive, f of c plus h minus f of c, this divided by h is less than equal to 0. So f of c plus h minus f of c divided by h is less than equal to 0. So basically what is this? This is basically the right hand derivative of a function at c, of a function at c. So I will write this implies right hand derivative of a function at c and which is less than 0. So if h is less than 0, then what happens? Then f of c plus h minus f of c divided by h, this will be now greater than 0. So this implies limit h tends to 0 negative and f of c plus h minus f of c. Now this whole term is greater than equal to 0 and this is basically the left hand derivative of a function f at point c. So from here I will write this implies left hand derivative of f of c is greater than equal to 0. Now since f of x is derivable in open interval ab, since f of x is derivable in open interval ab, this means what happens if f of x is derivable in this interval? This means that f dash x exists for all x belongs to open interval ab. So this also implies that f dash c also exists. Now right hand derivative of f dash c, this is equal to left hand derivative of f dash c and this is basically f dash c. So this implies that f dash c is basically equal to 0 for some c belongs to open interval ab. And this f dash c is equal to 0 because 0 is the common, I will write here reason, 0 is the common value of left hand derivative and right hand derivative. So hence the theorem is verified. Now I am going to solve one example on the Rolle's theorem. So first example is verify Rolle's theorem for the function f of x is equal to x square minus 4x plus 3 in the interval close interval 1 and 3. So first of all what we have to write, I will write here the function given is x square minus 4x plus 3. Now we know the three conditions and we will use these three conditions here for solving, or we can say for verifying the Rolle's theorem. So I will write, since it is a polynomial in x, so we know that since every polynomial is continuous, in the closed interval, I can write continuous function for real value of x for every real value of x. So this implies that f is continuous in closed interval ab, and here ab is basically closed interval 1 and 3. Second case will be that derivative exists, means the function should be derivable in the open intervals. So for this I will differentiate equation first with respect to x. So we get f dash x is equal to 2x minus 4. Okay, so which exists in the open interval 1 and 3. So therefore f is derivable in open interval 1 and 3. Third condition is the value of f at 1 is should be equal to f of f at 3. So I will find f of 1 is equal to basically 1 square minus 4 plus 3, and this is equal to 0. Similarly f of 3, this is equal to 3 square minus 4 into 3 plus 3, and this is again 0. So from here f of a is equal to f of b, or I can write or f of 1 is equal to f of 3. So therefore f satisfies all conditions of Rolle's theorem, all conditions of Rolle's theorem. So what happens? I will write here. So there exists at least one real number C which belongs to this open interval 1 and 3 such that f dash c should be equal to 0. Now f dash c is basically, so from here, from this equation, 2c minus 4, and this should be equal to 0. So from here 2c is minus 4 is equal to 0, or c is equal to 2c is equal to 4, or c is equal to 2. So clearly this point c belongs to the open interval 1 and 3, because 2, if this is the open interval 1 and 3, then 2 lies in between this interval. Hence the theorem is verified. Okay, so now I am going to solve one more example. So next example is verify Rolle's theorem for the function f of x is equal to sine 2x in the interval 0 and pi by 2. So first of all we will write what? Here function given is sine 2x. So I will write first part, since sine curve is continuous, we know that the sine and cosine functions are continuous. So sine function is continuous, therefore I will write f is continuous in the closed interval 0 and pi by 2. Similarly, second condition is derivative should exist in the open interval. So f dash x is equal to sine 2x. Derivative of sine 2x is 2 times cos of 2x, and which also exists in the open interval ab. So which exists in open interval 0 and pi by 2. So therefore f is derivable in the open interval 0 and pi by 2. Third condition is f of a is equal to f of b, or I can say that f of 0 should be equal to f of pi by 2. So for this I will find the value. So f of 0 is equal to sine 2 into 0, and this is basically 0, and f of pi, this is also equal to 0, sine 2 pi, and this is also equal to 0. So from here f of 0 is equal to f of pi. So we will write, since f satisfies all the conditions of Rolle's theorem. So what happens? I will write here, there exists at least one real number C which belongs to this open interval 0 and pi by 2 such that f dash C should be equal to 0. So now f dash C is basically, what is it? It is 2 times cos of 2C. I am replacing x by C and this should be equal to 0. So now I will find the points where cos is 0. So from here I will write 2 is not equal to 0, so I will write cos of 2C. This is equal to, now cos of, I know that cos 90 is 0. Similarly 3 pi by 2 is 0, 5 pi by 2 is 0, and so on. So from here cos and cos gets cancelled. I am left with 2C is equal to pi by 2, 3 by pi 2, 5 pi by 2, and so on. Now I will take first term, that is 2C is equal to pi by 2, or I can write C is equal to pi by 4. Now this C is equal to pi by 4 lies in the open interval 0 and pi by 2. So hence the theorem is verified. Hence the Rolle's theorem is verified. Thank you.